Okay, I'm getting back to the the topic 7 worksheet here. And on the first page, we had talked about inverse of a function. Problem 5 is where the exponential stuff would begin if you were to kind of compare that to the things that are in the 115 book. So this would be kind of where, section 5.3 would begin, the topic of exponential functions. An exponential function is a function of the form y equal a to the x. Okay, sometimes there's a constant multiplier, and sometimes not. Of course, the constant can be anything, right? Not 0, but could be a constant of 1. So y equal 3 to the x would be an example of an exponential. Okay, and I've got the graph of that curve. An exponential is always going to be, kind of taken on the shape of something where you see here where it's going to be kind of steadily rising, and then there's going to be at some point a drastic increase, okay? Or on the flip side of that, the curve could be drastically decreasing and then kind of flatten out a bit as it approaches a boundary. There is a boundary on an exponential, okay? Since x is in the power, 3 to the x will never return 0. Okay, now it's kind of hard to tell here, but this curve is never going to get to the x-axis. Okay, like there's an asymptote on the x-axis, since you'll never have 0 coming out of that calculation, and that's a feature of an exponential. There will always be a horizontal asymptote on the graph. Part A, write the equation whose graph is the graph of y equal 3 to the x, but is reflected about the y-axis and then shifted up 1 unit. All right, transformations. So if I'm reflecting about y, then I need to replace x with a negative x. And so I've done that. And then we're going to shift up 1 unit, means that I want to tack on a plus 1 after that 3 to the negative x term. Okay, so y equal 3 to the negative x plus 1, that would be the equation of this graph right here, but reflected about y and shifted up 1 unit. Part B, write the equation whose graph is y equals 3 to the x, but is vertically stretched by a factor of 2. Okay, vertically stretched by a factor of 2 means that I would just throw a 2 in front of the expression 3 to the x, and of course that would mean I'd multiply the y values by 2 on all the points on this graph, and I'd be stretching the graph out vertically. That would make the graph get closer to the y-axis there on both sides. Part C, write the equation of the horizontal asymptote for y equal negative 3 to the x minus 2. Okay, now here's y equal 3 to the x, our basic function. Okay, if I throw a negative in front of that, that means that I would flip this graph upside down to be reflected about the x-axis there, and then the minus 2 means that I would shift down 2 units. So all these points would be relocated, and that would include the asymptote, right? Initially, I have a horizontal asymptote right here on the x-axis. Reflecting the graph about f won't change where that is at, but shifting it down 2 units means that you're going to have a horizontal asymptote right here at y equal negative 2. Okay, so y equal negative 2 would be the equation of that boundary then on the new graph. Of course, make sure that you're writing this as an equation. Don't just write negative 2, because that could be misleading in that you'd be talking about x equal negative 2 or something, Okay, problem 6. Find c and a for the function f of x equals c times a to the x if f of 0 is 1/2 and f of 1 is 3/2. There's a couple of problems like that in the book where they want you to find an exponential function that kind of fits the information the additional information that's given to you. So f of 0 means that I'm going to plug 0 in where I see x. Well, I've done that. Anything to the 0 power is 1, so c times 1 is c. Now f of 0 is 1/2, so that would mean that c is 1/2. Okay? And here's the current form then that I have, knowing that c is 1/2. Now they're also telling me that f of 1 is 3/2. F of 1 means I'm going to plug 1 in where I see x, and so I've done that. I've got 1/2 times a to the first. F of 1 is equal to 3/2. In this equation, 3/2 equals 1/2 times a. If you multiply both sides by 2, you'll have a equal 3. So the function that we're talking about in this problem would be f of x equal 1/2 times 3 to the x. Now that would be a vertical shrink of y equal 3 to the x. Okay, you'd be smashing the graph and therefore making the curve split further from the y-axis on both sides. You would still get the new graph by multiplying the y values by 1/2. Okay, so transformations there. Now they're not asking me to graph anything, but that would be something that I could take away from this calculation. Problem 7, we're solving some equations. Now when you're solving an exponential, the plan early on should be trying to get the same base on both sides. Okay, now it won't always happen where you can get the same base on both sides, so there is more to know. But in these problems, we should be able to get the same base on both sides. In part A, okay, I'm going to solve for x. Now I know 7 squared is 49. So where I see 49, I'll just write 7 squared. Now I've got base 7 on both sides. And I can remove the 7s and set the powers equal. That puts me back on familiar ground now because I no longer have an exponential. I no longer have x in the power here. And I'm working with just a linear function, linear equation. Okay, if you subtract 12 and then divide by -5, x equal 2 would be the solution there. Part B, again, we're solving for x, and again, the plan is to try to get the same base on both sides. Well, I know 4 squared is 16, and I can get base 4 on both sides here. 4 squared to the x, I'd want to multiply the exponents, that'd be 4 to the 2x. And at this point, I can then remove the 4's and set the powers equal. 2x equal 2 minus x. If you add x and then divide by 3, we get x equal 2/3 as the answer. Okay, by the way, when you're solving an exponential, you don't need to check your answers for extraneous solutions. You can check your answers if you want, but you won't have extraneous solutions come up. Okay. Part C. Again, I'm solving for x, and again, I'll want to try to get the same base on both sides. The base is e, okay, or that's what I'm going to be shooting for here on the left. I'm going to leave the right side as is, with that being e to the 12th. On the right, e to the 4th to the x, that'd be e to the 4x. Okay, I'm just multiplying the exponents. And I'm going to multiply that by e to the x squared. Law 1 on that list of laws of exponents that I gave you in the 115 class said that whenever you have the same base and you're multiplying, you're going to keep the base and add the powers. Okay, so I'm looking at e to the x squared plus 4x then on the left. And knowing that I've got base e here on both sides, I can remove the e's and set the powers equal. X squared plus 4x equal 12. If you subtract 12 from both sides, you've now formed a quadratic. Okay, and again, that kind of puts us back on familiar ground here in that we have a quadratic now. This one's going to factor nicely. X plus 6 times x minus 2. So then when you set the factors equal to 0, we get x equal -6 and x equal 2. Here's another one, part D. We're solving for x. Now, anything to the 0 power is 1, right? And I can get base 9 on both sides here. 9 to the 0 is 1. And now that I've got base 9, I can remove the 9's and set the powers equal. Subtract 12 and divide by 3, and you get x equal -4. Okay. So again, the point of this is to say that when you're solving an exponential, try to get the same base on both sides. Okay, now it won't always happen where you can do that, and so we'll talk more about that later on in this topic worksheet here. Problem 8 and 9 are just kind of some application problems of an exponential. Problem 8, we want to find the future value of a $3,300 deposit at 3% for 2 years if the account pays interest compounded quarterly. All right, so here's the general formula for compound interest. A is the future value, so it's how much money you'll have down the road if you just let the money sit there and do its thing. P is the present value, which for us is $3,300. Okay, and then R is the interest rate, which is at 3%. R is going to have to be converted to a decimal. And then n is the number of times that you're compounding in a year. Compounding quarterly means that 4 times in the year we will gain additional interest on top of the interest that we've already made. Okay, and therefore would be 4. T is the time in years. We want to see how much money will be in the account 2 years down the road if we just let it sit there and do its thing. Okay, so I've got my numbers plugged in. 3% as a decimal would be 0.03. And if you type in 1 plus 0.03 divided by 4, I'm getting 1.0075. And you'd want to use all the digits that are available on the screen if possible. Like, I wouldn't do any rounding until the very end when you go near a cent. Otherwise, the numbers are probably not going to match there because you were rounding too early. So be careful about that. You know, for these problems, we want it right down to the penny. Okay. 4 times 2 is 8. And so then how I would type this is I'd say, okay, 1.0075 to the 8th. Hit enter, and then multiply that by 3,300. And we get $3,503.28. Of course, we're working with money, so go near a cent anytime you're working with money. All right, so that would be one application of an exponential. You know, we're working with exponents here. Problem 9 is another application problem. We'll do problem 9 and then we'll stop the video. The population of Nevada, okay, by the way, the population of just any population, if you were going to study you know, how it increases or decreases, usually it will involve a formula very similar to the formula that you see here, where you have an initial amount and you're multiplying that by e to some power, and the 0.014, that would be the exponential rate, we call it. Okay, that's a positive number, so we would understand this problem to be exponential growth, meaning that the population of this state is going to be growing over time. Okay. Now, the formula that is given to us here tells us the population of Nevada, which is in millions, and X is the number of years after 2010. So I would like to know an approximation of the population of this state in the year 2025. Well, it's been 15 years since 2010, so I would just simply plug in that number and go to the calculator now. Okay, if you type in just the exponent first, 0.014 times 15 is 0.21. Okay, so then how I would type this in here is I would type in E. Here's if you hit second and then the division sign, that sets you up with E, and then to the power 0.21, hit enter, and then multiply that by what was it, 2.7. Okay, and I'm getting roughly 3.3 then if we go nearest one digit. Of course, make sure that the units are in millions. You know, there's not roughly 3 people in the state of Nevada. Okay, roughly about 3.3 million people would be in this estimated living in that state in the year 2025.